Um,
Anybody else got a
the
beer? I know Tao doesn't because it's early.
yeah,
Cheers.
I've got
Oh,
a
no, I gotta go get one. I only have tea.
You know, we gotta we can go ahead and get started, and I'll just Tao or Matt, go ahead and take it away if you want to.
Yeah, I just wanted to show you real quick. But basically, we got together last Saturday, the whole group of us, and I think everyone here was actually there last Saturday. Yeah, so basically, we all got together and we looked through the documents that you sent us, and we used that as sort of our basis for what we were thinking for DACC, and we sort of compared it to what we already had done in our previous DACC hacks and figured out ways we can sort of combine those things together. So initially we were sort of looking at creating like a sort of modular version of the designs that you sent us, and through talking we realized that there was actually big advantages to using pre-built parts. So we actually started this idea of sort of working around using PVC pipe actually as our sort of main construction material, and that sort of led us to like a deck that sort of looks like this, and then we started sort of fleshing it out by filling it in with different components and building up a list of materials that it would take to make the various different parts of it. And so we're currently working on sort of fleshing that out and figuring out what all these different parts are, what they're putting together, and various different members of the team are sort of working on different parts of, let's actually like render this out and see what it looks like and see how fast we can advance this together. So we would really love your input on the designs that we're coming up with and your take on it. I know like in some ways it's very much inspired by the materials that you gave us, but it's also sort of going to be different and substantially in some ways because we're looking at sort of other things in terms of like readily available parts and keeping prices of construction fabrication down and finding ways to actually use off-the-shelf things that'll make it easier for people to find and build their own things. We actually came up with a document with like a list of questions that we wanted to ask you to help us advance, because a lot of our assumptions, we were able to get some of the answers from the videos that you had done and the interviews that Chris had done with you. But we were basing some of our assumptions on the sorbent that we have been working with, that we had found ourselves before, and we know that your sorbent is substantially different in some ways. So that's the reason we set up this call, was sort of so we could have a chance, an opportunity to talk through some of those questions with you. So we have a couple of people on this call who are much more versed in chemistry than I am. And so I think Peter's actually going to sort of take the lead on asking the chemistry questions. So yeah, Peter, if you want to just sort of dive in with some of the questions for Tao.
Sure. How long do we have? An hour total? 50 minutes left?
Yeah.
Yeah.
If anybody wants to stick around longer, we can certainly do that.
Sure. And first I want to say, nice to meet you, Tao. I've read many of your papers at this point. Good to finally speak. Okay. So one question is, how long does it take to fully load the sorbent with the CO2? And is there a dynamic curve that shows absorption over time for, say, that 1 kilogram per day unit?
Yeah, that's very important. Generally, it depends on the material, like the porous structure of the material. So, for example, at first, our material needed more than 1 hour. It's about 1 and 2 hours to finish, to fully load it, the CO2. And so that means actually, you know, for the absorption mechanism, we need 3 steps. The first step is CO2, we load CO2. The second step, we spray water, or we increase the humidity, and then the CO2 will be released. And the third step is we dry the material. But actually, in the practical operation, you just need 2 steps. The first step, if we start from the fully loaded state, right? You spray water and the CO2 will be released out. That is the first step. And the second step is just you begin to dry the material, yeah? And then actually the CO2 will be loaded gradually. So the drying process and the adsorption process will be integrated into the one process. They will happen simultaneously. So there's just 2 steps for drying and adsorption. So what the time, what I said is for the for the drying and adsorption. Yeah. So previously we need 1.5 hours to 2 hours to finish the step. And that is because of the dense structure of the material. And now we are developing more porous structures so that we can finish the adsorption process in like 40 minutes.
Okay.
Yeah. Yeah.
As knowing that you've combined these steps, as an immediate follow-up, does this now make that like scissor mechanism, the lowering thing, not necessary? I remember you said that was one of the more expensive components for your design.
Pardon? Which part you said?
After it's adsorbed, you have that scissor mechanism that lowers them and spreads them out, and then you spray the water over it. Does that preclude the need for that?
Oh, I see. Yeah. So that at first we hope we can use less energy as possible. Yeah, because yeah, and then we hope the material can be dried in the atmosphere.
Mm-hmm.
Like, yeah, so then we hope we can move the material, move the solvent to the atmosphere, to the outside. And then, you know, the solvent will be dried by the flowing air, and the CO2 will be loaded simultaneously.
Mm-hmm.
So you need to use pump to dry the material, right? Because Matt just showed your design. You put the solvent. Now you put the solvent in the container, and then for the drying process, you need the airflow go inside. You need a pump, right? So that means you need the electricity. And so at first we think we can avoid this by moving the solvent to the outside and use the nature air, because we measured the drying process and we found that the wind velocity of 1 to 2 meters per second is enough for the drying process. Then, in other words, if the wind velocity is higher than 1 meter per second, then there is no significant impact by the wind velocity. So 1 meter per second wind velocity is enough. But finally we found that because it may be because of the prototype, the first design, and if we have that part, we'll increase the cost of the material. Yeah, you use some you don't use the hand, use your hand to to move the part, right? You need some motor. Yeah, you need some electric motor to do that. Then that increase the total capital cost of the machine.
Right.
Yeah.
Okay. During the scrubbing process where you're spraying the sorbent layers with water, do you have an idea of how much water you're consuming for the flow of the whole thing?
Well, let me think. Generally, we need the same weight amount of water as that of the solvent. Like, for example, if you have 10 kilograms of solvent in the system, and generally you need about 10 kilograms of water for every circle to dry the material. But a lot of water can be recycled. I just mean the spring water. And how much water can be recycled is, I think, about 50% can be recycled. Yeah, so that is the current design. And of course, the water consumption is huge. So that's also
the other
very
50% to the other 50% you lose to evaporation.
Yes. Yeah, because the solvent will absorb water. And, when you spray the water. Yeah.
Tao, I had a question about your current design, the one where the one that we saw in the video where you were exhausting the CO2 gas into the greenhouse. How is that being dried? Do you have like dry air, like kind of processed dry air coming in to dry that out, or is it just exposed to atmosphere and so it's just kind of whatever air is in the lab is drying out the sorbent? How does it
During
work
the
right
dry,
now?
yeah, during the drying process, you just need the atmosphere air. Yeah, of course, if the humidity in the air is high, it will decrease the capacity. Yeah,
Thank you.
yeah.
Well, we got underwater. I might as well just continue with that. So just to clarify, your system is mostly a closed loop that's being replenished by the losses from evaporation, or are you just taking tap water or DI water, or kind of like what are the complications associated with water quality and source?
In our lab, we use DI water, but uh, in the practical running, tap water should be all right.
Cool.
There's a chloride ion in the tap water, right? But the concentration is quite low. We calculate that maybe you can use that for 1,000 times. After that, maybe if you want to regenerate the solvent, because the chloride will be, there's an ion exchange
Yeah.
material. So if you think the capacity is decreased because of the chloride exchange, and then you can use the alkaline solution to wash and regenerate the solvent. Yeah, that means the solvent can be regenerated, even you use the tap water, it can be regenerated.
Okay. And do you, in a closed loop system, do you know how much of the CO2 becomes aqueous, and do you monitor pH as a result?
That's also, that depends on the design. That means how much solvent is loaded in a fixed volume, right? Yeah, so as current design, at the current material, the prototype is designed for the greenhouse. So we hope it can be 1,000 ppm, like 5,000 ppm. That should be all right. Should be enough. I mean, yeah.
Okay. I'm curious about I know the technology that you've developed involves spraying these sorbent cartridges. I'm curious about efficiencies of different watering methods like direct submersion or misting, and what differences in performance, like effectiveness, time, complications you would expect between different methods. Especially, I know this is designed around a greenhouse, but of course there might be options for mineralization, at which point you need to get the CO2 dissolved anyways.
Mm-hmm.
So I'm wondering
So
if you have any experience with that.
you mean how can we get to the CO2 with different concentration, or?
No, and I mean, instead of like, because we have to build the component parts, and instead of
Yeah.
nozzles that turn on and spray, if instead an alternative would be just to submerge and dunk the sorbent
Mm-hmm.
and then raise it back up.
Mm-hmm.
I believe you had some previous designs that were doing that, right? The Tao, you had some that were just like submerging the sorbent rather than spraying it. Is that correct?
Oh, okay, yeah. Because that, as I said, we hope to fix the solvent, right? We don't want to move the solvent module. So currently we use spray water. Yeah, and of course, if you immerse the solvent into the water, that will be very quickly just inside and then take it out very quickly. So that will be very just about seconds. Yeah, and spray water is also very. I think it's very efficient. The time is like 1 minute should be enough. Yeah, but if
1
you
minute
just
of spraying water.
yeah. So, but if you want, if you use the very high in very high humidity air, like I mean, if you want to evaporate the water, and then the water absorption process is quite slow. Maybe you need
Okay.
half an hour. Yeah, so that's different kind of the the moisture process.
Okay, so very long for spray, 1 minute. I'm sorry, very long for like mist or saturated water,
Yeah.
saturated air. 1 minute for
Yes.
sprayed, and maybe something similar for submerged, or would it be kind of almost
Yeah.
instantaneous?
Yeah, for practical operation, you immerse the into water and take it out. Yeah, maybe one minute. Yeah.
Okay.
No.
Okay. Um, do you do you know how adversely affected the functional group of the sorbent is to pH, or how sensitive it is? I know it has quaternary ammonia groups, which are pH sensitive.
Uh-huh. Well, I haven't considered about this, but you know, uh, for the algae, you know, the algae is also kind of plant which they need CO2, right?
Yeah.
For the algae, they currently use they do not of course they use the gas CO2, yeah, to feed the algae, but actually the algae can also be fed by the sodium bicarbonate solution.
Right.
You can imagine that there's a CO2 in the sodium bicarbonate.
Yep.
Because it is formed by CO2 and the sodium carbonate.
Yep.
Right? Yeah. So our material actually can also work under the pH swing of sodium bicarbonate and sodium carbonate.
Okay.
Yeah. Yeah.
Okay.
And you can check the pH of that. Maybe
It's like 6.3 to 10.3 or something like that.
Yeah.
It would be slightly
Yeah.
basic, which would be,
Yeah.
I think, in the ammonia, not ammonium switch between that species, which that's why I'm bringing it up. I think that could be problematic.
Yeah.
Anyways.
Yeah.
Okay. So let's see.
And
that
actually, the material can work also at a very strong alkaline
it can.
atmosphere.
Okay.
Yeah, like sodium hydroxide.
Oh, wow.
Yeah,
Okay.
yeah, it can work, and there's it won't damage the material.
Excellent. Okay, great.
Mhm.
So the question is, how much does relative humidity affect CO2 adsorption? And should we be carefully measuring this? At what relative ambient humidity is the air dry enough to dry the sorbent? And I think that could be bundled together with the notion that I think you're working on like newer, more tolerant sorbents that can tolerate 50 to 60%, which would be much better than the ones we've been looking at, which are, I don't remember, like 20% max. So that would probably open a lot of doors for this.
Yeah, for most of the solvent we tested, yeah, they can work. I mean, they can keep the over 80% of the capacity and the humidity lower than 60%, relative humidity of 60%. Yeah, they can keep over 60% of the maximum CO2 capacity.
Okay.
The maximum CO2 capacity is estimated from the ion exchange density of the material. If you understand that, because the ion exchange density is designed from the fabrication factory. Yeah, once the ion exchange material is fabricated, the ion exchange density is fixed. Yeah, like 3 mole per kilogram of solvent. That's the ion exchange density. And you can calculate the CO2 capacity. There's from the ion exchange density. So you have theoretical the maximum CO2 capacity. And then of course the relative humidity will impact the practical capacity. And for our current design, if the relative humidity increase to like 80%. Yeah, 80% relative humidity, and the CO2 capacity will be decreased to half of the
Okay.
maximum.
At
Yeah.
80% is only, I would have thought it'd been, at 80% it's only half, it's still half effective?
Yeah, it is a fact, but the capacity will be cut by for half.
Sure.
Yeah.
So 3 moles per kilogram, that's 132 grams of carbon dioxide per kilogram of sorbent. Is that what you're saying? That's the max capacity?
The max capacity is like the ion exchange resin has the 3.4 mole per kilogram of ion exchange capacity, and that equals to 1.7 mole CO2
Ah, okay.
per kilogram of resin.
Great. That's
And
gonna
then
answer a lot of
you
questions.
use, yeah.
Cut our list in half, guys.
Can you repeat those numbers again? Sorry, I'm just trying to make sure I write this down.
Thanks, Kristen. I really appreciate you staying on top of that.
I will explain, because the ion exchange density means the ion charge density, like chloride. It is the ion exchangeable, right? So that means the chloride is a kind of ion, the hydroxide is a kind of ion. So at first the ion exchange density is 3.4 mole per kilogram of material, and two groups of anion can capture one CO2. So the CO2 capacity will be half. This is 1.7, right? 1.7 mole per kilogram of solvent. And then you use some material like the paper or polymer to support the ion exchange resin, because it is powder, it's very fine powder. And then if it's a supporting material, the ratio of supporting material and the ratio of supporting material to the resin is 1:1. And then the CO2 capacity will be cut by half again, right? That is about 0.85 mole CO2 per kilogram of the shipped material, shipped of the solvents. Yeah.
Okay.
So that's the final capacity, the maximum capacity. Yeah.
Okay.
And actually, the climate will use amine-based solvent, right? So you should carefully about the capacity, because if we publish paper, generally we use some higher capacity. That means the amine capacity, right? But they need some supporting material to support the amine. And when you use the solvent, actually that contains both the supporting material and the amine. Yeah.
That was awesome. Next question.
Yeah, that was like very helpful. Thank you.
Yes, that's like literally cut the list in half.
Yeah, because if you just read papers, you will be confused. Some capacity is high, some capacity is low. But the capacity, because in the lab, the scientists use the very thin, very fine powders as a sample to measure the CO2 capacity. But for the real solvent, you cannot use the powder, and so you use some supporting material, to support the material. Then there's another capacity unit.
And you think most sorbents have that 1:1 ratio of the sorbent to the resin? I mean, like the sorbent to the substrate it's grabbing onto is about in a 1:1 mass ratio?
Yeah. Yeah.
Most of them, okay. Because the
Yeah.
data that we get, like we have one from Sigma, but like, you know, it's not the most complete data set for what we're trying to, the information that we hope to get from it. So if we can get some kind of like general rules of thumb for these things, that would be helpful in, you know, planning and designing.
Yeah, there's another technology which can fabricate, we call it homogeneous ion exchange membrane. That means basically most of the material is resin rather than the supporting material. But I think they will also add some like fibers to increase the strength of the material.
Like
Yeah,
rebar.
so that depends. Yeah.
So if I can just hop in, so if we were to assume then, just from a mechanical perspective, if the resin beads that we have from Sigma right now are a heterogeneous construction with a core resin bead and then some amount of the sorbent material on the outside of each of the beads, does that mean that the sort of like, there's a permutation capacity there? So like if two resin beads were like touching each other, the portions that are in contact are not going to be exposed to open atmosphere, but we should be able to assume that the portions that do make contact with open atmosphere that are contacting CO2 will be able to kind of pass that on to deeper segments as well as the parts that are being obscured from points of contact.
The raw ion exchange beads had the size of 100 micrometer, like 500 micrometer, 500 micrometer. That's too big. So generally we will grind it into fine powders like 50 to 30 to 60 micrometer. Yeah. And then if we use the polymers, we embed the micro beads into the polymers, and they are just apart from each other because they're embedded into the polymer. Yeah, like embedding to the PVC. You can use the PVC, yeah, to support the powders, and they are just the particles are just separate from each other, and the gas will diffuse from the supporting PVC first, and then contact with the surface of the resin, and then reaction inside.
I think we have to learn how to do that. The DACC sorbent we got over the counter it's pretty much 400 micron beads. I think we weren't aware that you're pulverizing that and then adhering it to something else, which would explain our numbers. It would be good because then we're gonna have a lot more surface area for what we need.
Yeah, yeah.
Yeah, so to be clear, you're like taking the sort of sorbent beads and you're like grinding them up and then spreading that out with the, but so maybe this is not the best question, but then the material ends up being a combination of the sorbent that's on the surface of the beads and the surface that the beads themselves are made up of. Is that correct?
Pardon? Your question is about the.
If you're grinding up so there's the supporting material that is like the bead that the sorbent is layered on the outside of the surface. If you pulverize it, then you have like a fine powder that's a mix of the sorbent and of the material the beads are constructed from. But that is what you want in the situation. I'm just a little bit confused about that.
Oh, the ion exchange beads is just a pure resin. They do not need supporting material. It's just a bead. Yeah, and then
Ours is different.
It is. I'm not actually sure. Is it like maybe we just got pure resin that just happened to be into beads, and we were under the assumption that we had a substrate, but there isn't one, and now we need an extra process to stick our new pulverized DACC stuff or whatever we get sorbent to a substrate.
Yeah, I think it's. I don't think it's. I think the assumption that there's a substrate Yeah, I don't think there is a substrate. I really do think it's just the pure resin in bead form. And one of the reasons I suspect that is when we were digging through and looking up which beads we wanted to get, like we basically got the ones that were the most porous. So like they had the least cross-linking. So we got the resin with the lowest amount of cross-linking available. And yeah, there's no substrate mentioned. It was just less cross-linking for bigger.
Cross-link the structure.
Yeah.
Oh,
Okay.
that's great news.
Okay,
for
that
budget.
is not what
That's awesome.
yeah, that is very different from what I understood. So that's great to know. Yeah.
Yeah, I mean, we can go back and look at the material data sheet stuff again, but I'm pretty sure that's accurate.
Okay. They were just so uniform in size. We were kind of assuming that they were just, it was a bead that was coated, but it's just a bead of the whole material.
Mm-hmm.
Okay.
Yes.
Great. Whoever has the sheet open, I believe A4 was answered. Is that correct, or am I mistaken?
A4, what does the CO2? Oh, I didn't actually take notes on that. It might have been answered.
I don't think it was, because I was listening for that one specifically. So after you have like submerged the resin and it starts to release the CO2, is it concentration driven? Does that mean like right at the beginning, once it has been wetted, that the rate at which it'll release the CO2 is highest immediately after and will taper off?
Yes.
Okay.
Yes. Yeah.
Is there any sort of like established curve? One of the things that we've been trying to figure out is based off of our sensors, we want to make sure that we're actually witnessing that sort of exchange happening where it's releasing the CO2. So I was just curious, like how much of a rise percentage-wise should we see within the first 5 minutes, 10 minutes, 30 minutes, just so that we can kind of track that curve over time?
Well, first, it is true that the desorption rate will decrease with the time. So at first, you can see a lot of CO2 is released from the desorber, and then the desorption rate is slow down. And generally, let me see how generally it's be measured in an hour. Yeah, most of the CO2 will be released. I mean, actually, it's also depending on the concentration or the concentration of the stripping gas. If the stripping gas is nitrogen, right, so it will take a longer time, like maybe 2 hours to dissolve all of the CO2. But the stripping gas is like just atmosphere air, and 1 hour would be or enough for the desorption.
Yeah, one of the issues specifically that we have is we don't have a lot of the resin. And so the concern is that even if we were to saturate how much of the sorbent that we have, that the peak effect might be within the range of the noise of the sensors that we possess. So it would be ideal if there was kind of a predictable spike, let's say maybe from the time of submersion, maybe it takes like a minute or something, then we can expect a certain sort of like spike around that time. That was just kind of the question so that we could better anticipate what the dynamics would be over that 1 hour drying period.
But now that we know we have the whole volume and not the surface area of those beads, we have a tremendously larger amount of.
That's true too.
But also, I mean, I think the real key is like, are we going to be able to have a sensor that monitors the change in ppm? It seems like what you're saying, Tao, is that you're getting each release cycle. There's like 8 release cycles a day. They get you about to 1 kg per day. But each release cycle, you should have a spike at the initial when the sorbent is initially exposed to water. That should be your highest concentration of CO2, and then over the course of an hour, it'll sort of ramp down. But at the initial thing, you'll see a huge spike in CO2, and then sort of ramp down over time as it releases more CO2. Is that correct?
Yeah, the maybe in the first first several minutes will be you can see a peak, yeah, and then it decreased actually very quickly, and of course depend on the how much solvent in a fixed volume.
So
It also depend on the loading density.
we've got about 40 grams total. Is that like way under what we would need?
40 grams.
Um,
You
I
have
know
40 grams of the resin,
correct.
and you use the resin without grinding.
We did.
You
We
grinded
will,
it.
but we did.
We did not grind.
Oh,
No
yeah,
grinding.
because if you just use the raw bees, you will absorb very weak adsorption.
Right.
Yeah, yeah.
We observed that.
So I suggested the grinding into like under 100 micrometer at
Mm.
least. Yeah, 30 to 60 micrometer is good. And for 30 gram, I think there's a lot. You can do a small test with 30 gram. You can make a very a small PVC tube with a centimeter with diameter of 1 to 2 centimeter, yeah, and like 10 centimeters long.
Mhm.
That would be a good. That size would be a good.
That's
reaction.
actually a really good idea. Let's make like
Yeah.
a super mini DAC for testing
Yeah.
purposes
Yeah.
with the stuff we have. I like
Yeah.
that
And
idea a lot.
Yeah, this sounds
Mhm.
very similar to the columns that we were using.
Oh, but yeah, but on the other side, you cannot do the water spray with the powder. It will be very fine powder, and when they immerse that into the water, they will just you need the filter, very fine filter to avoid the lossage of the material. Yeah.
Do you have any papers or techniques or anything on how to adhere the resin to like the plastic substrate that you use?
We have a paper to explain how we disperse the solvent into the PVC.
Ooh, that would be fantastic. If we could
Yeah.
do that.
Yeah. If you cannot find that, let me know. I will send to you.
Great. Thank you.
Yeah.
Yeah, I'm sending you an email right now. Just attach the paper to that email, okay?
But you need chemicals. You cannot do this in your home. You need to do that in the lab.
What do you need?
Yeah.
He was like, I'll put
It
it
is
in my
all
home.
set in the paper. Yeah.
Okay, we'll
Yeah.
check it out. And before we leave that topic, the sorbent we got is chloride ion quaternary ammonia based, just like the ones in your paper. I performed the step to swap the chloride ion out with hydroxide that under your materials, but I have no way to test if that was successful or not.
Mhm.
I'm in that. I don't like. I followed it to the letter of what you did, but I don't know. I can't. I guess it wasn't pulverized too, so that's probably not good either. You know how you cook it in like 90 degrees Celsius water for 48 hours,
Oh.
and then do some sodium hydroxide washes.
Yeah.
I suppose I would have needed to have pulverized the beads in order to expose them. Is that right, or do you think it worked without it?
The heating process is to expand the
Yep.
the resin beads, to increase the pore space inside.
Okay.
Yeah.
Okay. All right. Where are we? Okay. I guess maybe we should move on to airflow. A question is, and again, like we've answered kind of half of these already just in conversation, but can this process be done with passive air? Do we need fans? 1 meter per second wind velocity enough? I think
That is what I tested. Yeah,
that is okay.
1 meter per second is enough. Yeah,
Okay.
that enough means the wind velocity across the surface area, across the surface of the solvent. But if you have many layers of the solvent, you can imagine that in a large machine, you have many layers of the solvent.
Mhm.
So you very good design, engineering design, to ensure the wind velocity at every layer of the material. Yeah, that is very important.
Okay.
Yeah.
And it appeared that your original design had 2 fans. Is that the question? Is why does the original design have 2 fans versus 1, like an inlet fan?
Because you need one to blow the air into the solvent. That is the simultaneous drying and adsorption, right?
Mm-hmm.
Yeah. So if you calculate, because I just said you need 1 meter per second of velocity, and you will find that you have a large the volume needed. Yeah, you need a large volume. Yeah, and for the second step, for the desorption step, you need to pump the CO2 into the greenhouse, and that is the concentrated CO2, like 1,000 ppm or even 10,000 ppm. So the flow rate is lowered by 1 to 2 order of magnitude. Yeah, so the volume rate is not matched for the absorption and desorption. So generally you need 2 for that, 2 pumps for that.
Okay.
Yeah.
Sorry, for the construction of your unit, so your inlet fan, which you're primarily using for drying purposes, was a higher output fan, and then you had an effluent fan that you were using to pump the CO2, which was a low flow rate to maximize concentration, and that's the reason why you had 2 fans.
Yes.
Cool.
Perfect.
So the inlet fan is
actually
only running. Sorry. Just to
the fan
clarify.
I said is inexpensive. Yeah.
So
Yeah, just maybe 100 of IMB, but thousands of IMB. Yeah, it's quite cheap.
And so the inlet fan is only running during the drying process. It's not running throughout. Is that correct?
Right.
Cool.
That's correct. And the inlet air is also different for the 2. I mean, the inlet stripping gas is also different. For the drying and the adsorption process, the inlet stripping gas is air, ambient air. For the second step, actually you can just cycle the air in the greenhouse. Can you imagine that for the desorption process? Yeah, you can just cycle the air in the greenhouse. Yeah. There's an inner cycle. You can imagine there's an inner cycle. Yeah, so no CO2 will be released out.
That's so good.
Yeah.
So okay. So it is capturing passively though. Just to clarify, when it's capturing CO2, that is a passive process.
Mm-hmm.
Okay.
I had a lag. Chris, I think the next question is yours about air pressure.
Yeah, so that kind of answers the question that I had. So but I just wanted to kind of specify and clarify about your current design. So the way that the cartridges are designed, you've created these sheets that have the crushed up resin embedded on these sheets, and they are oriented parallel to the direction of airflow through the system, right?
Mm-hmm.
So if that's the case, then is it, because you're grinding up the resins and their like internal volumes are minuscule, is it that the air air just kind of flowing past is sufficient to kind of refresh it with a high concentration of atmospheric CO2 in order to capture as much as it can. Because the thing that we were kind of concerned about or were curious about was like, would it be necessary to kind of like force the air around each of the bead segments, which I think we've kind of answered based off of his previous answers. But yeah, I guess there's like a couple of questions that have already filled in some of those gaps. The fact that like when you have a crushed up resin segment that's been embedded on whatever support material, it will diffuse across the entire volume, correct?
The entire volume of the supporting material?
Oh, no. So if you had the original bead, it's now crushed up into kind of small pieces. But the kind of like the 50 micron piece that you embed into the surface of the PVC, you don't need to make contact with air on all sides. It'll diffuse through the volume.
No, they are, because like, for example, the size of the granite bead, the size of granite powder is 50 micrometer, right?
Okay.
But the thickness of the shipped the solvents is like could be 1 millimeter.
Right.
That is 220 times. 20. 20 times the size. So most of the solvent, most of the powders will be embedded inside.
Sorry,
inside of the solvent.
Can I, maybe it'd be helpful, I'm gonna just screen share to draw what I'm asking. If this is the support material, and then let's say that there is a like jagged piece of the resin that has been ground down, then there is some sort of adhesive that is going to make this portion of the resin inaccessible to atmosphere, right? So if this has CO2 over here, will it kind of absorb into the entire volume of the portion that's embedded? Because this would all be kind of hidden by the adhesive and the PVC. So it will diffuse through the volume of the resin?
Of course, because there are also some beads inside the PVC.
I see.
Oh.
Yeah, there are most of the powders that are embedded inside the PVC.
Huh.
So it won't just adhere to the surface; it'll actually absorb into the body of the.
Yeah, it will diffuse the air or the CO2 will diffuse into the PVC because it is not a dense structure. The powders and there will be gap between the powder and the PVC, so the air will be diffused very easily inside, and the 1 meter per second velocity is tested for this kind of structure. Yeah, so the gas diffusion is very high efficient.
Is there a way to like say like what percent of the sorbent mass is accessible to air under this technique? Could you say like not like 90% of the volume of the sorbent is accessible if we were to adhere this pulverized sorbent to the PVC?
You mean
I stated
the
that
solvent efficiency, you said? You asked?
Like the
Peter, I think I can draw what you're asking. When it's been adhered, is this surface area like 90% or is it like 10%? Using the technique that you've described, like the total surface area of the
total surface area of the resin powder, right?
What portion is exposed to atmosphere?
I think less than 10%.
Oh, okay.
Right. Yeah. I mean, directly exposed to the air, and there are a gap between the powder and the PVC. Yeah, but for the directly exposed surface areas, I believe it's less than 10%.
Does that include the nanotubules and the microtubules and all the ways you're able to provide more surface area I just looking at your electron microscopy shots, you know, there's holes in it to increase the exposure. Does that tend
Right.
to include that?
That doesn't include the inner structure. I just the outer surface. Yeah.
Okay.
Yeah.
Okay.
Because the thickness of the solvent, you can calculate the thickness of solvent is 20 times larger than the size of the micrometer. Right? Yeah. And they are mixed very uniformly. Yeah. So you can calculate that. Only a small part of the resin beads is at the outer surface.
But there's the atmospheric air can still access parts that are deeper than the outer layer, right?
Mm-hmm.
And so the total exposure to the atmosphere is less than 10%, or it's higher than 10%?
I think this is less than 10%.
10%? Okay. Okay.
Yeah.
All right. Another air question. This one should be pretty straightforward. I think it kind of also half answered.
I think the lower velocity should be enough.
Okay.
Yeah. Yeah, and I said 1 meter per second actually is it's not the turbulent
It's not
range, right? Yeah, yeah,
Baffles, but
yeah, yeah,
okay.
yeah.
B6, Chris, do you feel comfortable with that one? I think that's yours.
Yeah, that's good. We're good.
Okay.
Before we, I don't know if I want to derail this yet. I mean, I know we're going to head further into the sorbent and sorbent cartridges, although we've answered a few of these. So I don't know how much time do we have left?
What?
Technically, we're 4 minutes over, but it's Friday night.
Now, how much time
You have a lot of questions.
Yeah. Now, how much time do you have left? Because we have no reason to stop unless you want to stop, I guess is the way to put it. Tao, you there?
Yeah.
Yeah. Can you keep going for a little while or no?
Yeah, of course.
Just let's keep talking until we get bored.
Yeah.
Okay.
If you needed us to go, tell us that you needed to go. But
Get up
Yeah.
and-
we'll probably
I'm
keep
all
going
right.
for a while if you're ready to keep going for a while.
I'm all right. It's a labor holiday in China.
May Day. That's
Yeah.
right. May Day here in Costa Rica too.
Yeah.
Okay, sweet. Once we get through a couple more of these sorbent questions, I want to add a diversion. So I'm just going to add a couple more questions down here, but keep going.
I think you answered this. How much sorbent was required for your 1 kilogram per day? I think you said 10 kilograms, right?
1 kilogram per. Let me see.
I mean,
1
sorry, 1 kilogram of carbon dioxide captured per day. How much sorbent did that require?
I think less than 10 kilograms. What's the number I
think you said 10
I calculated last time?
I think you said 10 earlier, but I could be mistaken.
Is it 10?
I thought you said 10 kilograms of
calculate.
sorbent.
Oh yeah. I think it's similar. Yeah, quite close.
Okay.
Yeah. 10
and then I guess like a money question. We're kind of starting to build a list of materials or a bill of materials, and if I'm looking at 10 kilograms of our DAO wax, that's something in the order of extremely expensive. It would be
Really?
yeah, thousands. I can't find
The
it
resin,
open, but
the resin, the price of the resin in China is like 1,000 RMB per ton.
per ton?
So so how much ton do you need? How many tons do you need?
1/100th of a ton.
Yeah, yeah. In China, it's several, like
Okay, we're gonna put
5,000
That's
or
150
10,000
bucks.
RMB, yeah, per
So
ton of their resin.
okay, so is this the resin? Is this the resin that you're using? Is this
Yeah, I have from 2009. I I stayed in China, and of course I purchased this in China.
How many tons have you purchased?
Oh, no. I purchased the Bio University for the lab, but I mean, this is the market price for the massive requirement.
Okay, we'll have to rethink our supply chain for that, because that's like
Yeah.
a several orders of magnitude cheaper. Okay. Wow. All right.
Is that something that we could get? Is that something that's available for us to get in the US? I mean, maybe not now, maybe it would have to be another time, but or we could like order to NYU Shanghai or something like that. Is there a way that we can order the same sorbent that you're using?
If you just need like kilogram of solvent, you right, you need to do that. But if you really need tons of the material, of course, you can order that from China.
Cool.
You
Yeah, I think eventually that's the plan, but for testing purposes, kilograms
Yeah.
would be sufficient.
Yeah.
Or tens of kilograms, but
Yeah, and generally, if you buy only kilogram of the material, the price will be very high. That anywhere.
sure.
Yeah.
Sure. Okay. The next question's been answered. Next question's been answered. Next question's been answered. That's also been answered. Oh, and that's been answered. Okay. Is there a list of moisture? Question is there a list of moisture swing sorbents that we can get, and how and when? And I guess maybe some suggestions on the best sorbents to use and sources for them. It's kind of
Peter, can I inject something into there as well, just based on a previous conversation we had with Tao? So, Tao, it would also be interesting. You had suggested this in a call that me, you, and Matt had a few weeks ago about, obviously, your sorbent is very high performing. You've developed at your lab. So it would be interesting to know sort of how easy it is to sort of produce the sorbent that you've made, right? So like we obviously want this machine to be able to use multiple sorbents, but I'm wondering if you can give us some insight into how easy it would be for us to actually sort of reproduce, the sorbent that you've actually developed. If that isn't done.
So that is what I'm thinking, and then I suggested maybe the PVC is the for you. Maybe it's the most simplest way to fabricate the solvent, the current of the PVC. Yeah, because of course we tested different kind of substrate, and we think some of the steps may be a little bit complex. Yeah, for you, but PVC, I think, for the material and for the fabrication process, should be simple. Should be very simple. Yeah. And the performance actually is not only dependent on the resin base. It depends on the size of the powder, like how fine you grind the material, the bead, and it also depends on the the substrate and the inner structure between the substrate and the powder, so that we talked about the gas can be diffused inside very easily. So these are all very important. Yeah, and that is also the optimization research I'm doing in my group. But if you want to try the fabrication, I stress the PVC at the starting, and then you can understand the physical process.
Mm-hmm.
Yeah, yeah.
Is it possible to make the size of the particles too small? Like if you're using 50 micron, is there a pro or a con to making them like 20 micron in diameter?
Of course, you can try this if you have a kind of a resin called porous resin.
Okay.
Which they already have pores inside the resin.
Oh.
And then you can try like 100 micrometer. And even you can also try to use that bead directly without substrate. Yeah, we try that, but it's associated because if you just use the pure beads, the resistance, the flow resistance will be very high, right?
Okay.
And it will increase the power of the fan.
Okay.
Yeah.
So Tao, I had a question just from, so the thing that I'm kind of still fixated on is how we can either replicate or kind of replace your adherence method, because it seems like in order to get the ground up beads, whether they're ground up or otherwise, adhered to PVC, it requires us to use some sort of chemical process that you won't be able to do at home. And that's going to be a huge sort of roadblock that's going to keep somebody that's interested in producing one of these machines for their own home from being able to do that if they require facilities that they don't have access to. So I was wondering if you could just take a second to explain some of what's in your white paper. What is it about the process of getting the resin to embed into the PVC that requires specialized equipment or specialized chemicals? And are there alternatives that you could do with stuff that you could buy commercially?
Oh, okay. Yeah, so there are two kinds of the methods to fabricate the stripped film. Yeah, it is see in the paper. The first method is we described in our paper. Like for you, I will use PVC as an example. The PVC you purchase is a kind of PVC particles, like very big particles, millimeter or even centimeters large. And then you use organic solvent to solve the PVC powders into the slurry as a slurry. Yeah. So once the PVC is dissolved into the organic, it will be kind of slurry, and then you you pour the resin beads inside and mix them, right? And then you have a slurry of this kind of material, and then you can put the slurry onto a very flat surface, and then you can use it to make a membrane. So that is what we doing in the lab. And the organic solution has some it's kind of harmless. It's harmful to the human health. So you should do that carefully in the lab. Yeah. So that is the first method. The second method is called the thermoplastic method. Yeah. You have the PVC, right? You have the PVC. Also, you start from the PVC bead, and when you're heating the PVC, it will be soft, and then you can make it as flat. And if you mix also at this stage, you can also mix the resin powder, the grounded powder inside, and mix and yeah, and then
Mhm.
you just we call it extrusion process. Yeah, yeah. So by the extrusion process, you can make a PVC flat film. Yeah,
Cool.
but
So-
you need to
Interesting.
control the temperature very carefully. If the temperature is like over 140 degree, yeah, it will damage the resin bead. Yeah.
Oh, okay. 140 degrees Celsius.
Yeah, yeah, Celsius, it will damage the bees.
Mm,
Yeah,
Interesting.
and maybe it
Interesting.
can stay that for a very short period, like half minute or 1 minute, but too long time and the 140 degree will damage the bee. Yeah.
Is it
But
the? Oh,
but
sorry.
but yeah, but the thermoplastic need temperature like 120 degree to 140 degree, so you should carefully control the temperature. Yeah.
Is it the chemistry that breaks down at higher temperatures?
Yes. Yes.
I see.
Yeah. The chemical structure will be damaged and very high temperature.
120 is the max. What's the minimum?
140 is the max.
140 is the max. What's the minimum?
140. Yeah, but this depend. Actually, it also depends on the time. Like for like several seconds, of course, you can maybe do that, and like 150 or 160, but it shouldn't be very long. Yeah.
Is this process in your paper?
Oh no, you can find that in the patents. There's a lot of patents talking about this massive.
Mm.
Are those accessible? Sometimes they're hidden for a while.
The patent, yeah,
Okay.
that is accessible. Yeah.
Okay.
So this one is described in, this method is described in patents, right?
Mm-hmm. Mm-hmm.
Okay.
This is a mature industrial process.
Mm-hmm.
So one of the things that we were looking at was suspending the resin beads into a basically like an exoskeleton. We have a source for an 80 micron mesh. So we
Although
won't be
could
able to
go
get it.
smaller, right? That there was
80 micron.
was that does
Yeah,
that
that's the 0.08 millimeter. That's the finest one that's available
That was the
on
finest one,
Misumi.
Okay.
Yeah. So at 80 microns, we won't be able to get down to the 50 microns that your process recommends. But even if we were able to get even remotely close, we'd be able to grind up the resin and then potentially put something like a paper or mesh filter and then something else on top to kind of support this material. I just wanted to kind of pick your brain about if there's sufficient like potential for let's say that you have like a resin core and then you've got 2 sheets of filter paper and then some sort of support structure. Would you expect something like filter paper to allow enough atmosphere to penetrate through that medium that you would expect even reasonable or acceptable CO2 absorption?
Oh, if you use that kind of sandwich structure, of course you can do the adsorption, but we try that. But the I have to say the drying process will be very difficult because all the beads will be
right
fixed together by the water with the water, and that will make it very hard to dry. The material, like maybe you need 1 day.
In wet filter paper doesn't allow water flow.
No, it does not.
Yeah, for the extrusion process, I mean, for the 2 methods I introduced, the fine powders are just separate from each other. Yeah.
Do you have any suggestions?
Separated by the separation.
So imagine somebody just has access to whatever they can buy in the stores near them. And given the sort of like potential health hazards of trying to chemically dissolve PVC to create the slurry to embed the resin, what might you recommend for somebody trying to create the sort of like structure at home to support the resin and then wet and dry optimally or even close to optimally?
yeah, there's a very interesting idea. Let me explain. I haven't tried that, but I can suggest you thinking about the paper making process.
Okay.
I think we can do that from paper making process in
Oh.
our home, right?
I
Yeah?
make paper. That's one of my things. I
Are
make
you
Really?
really? That's
Yeah.
awesome.
So try. So please, if you are interested, you can put
awesome.
the resin powder into the slurry, the paper slurry.
Okay.
And let's see what
Oh,
you can make.
Ooh.
I could do that
Yeah.
tomorrow.
Wait,
Right.
can you say that again just so I understand it? We're saying a paper slurry?
Mm-hmm.
Yeah, the paper
Paper pulp
making.
is a great mesh.
Paper
Yeah,
pulp.
I haven't done that, but maybe. Yeah,
I will report back.
Yeah. Great. Yeah. But please.
I like that.
Use some.
Yeah, that's
material
actually
which
really
can-
cool.
That's super DIY. You need pulp, water, and a quick
An old
golden
Amazon
deco
box.
that you can make. It's very. Anyone wants to
suggest-
learn, just come to my shop.
I suggest you select the water. What you said? Waterproof the paper.
Oh yeah, that's true. That would be an issue. Yeah, I have to figure that one out.
Yeah, if you immerse that into water or spray into water, you
Okay,
do not expect it to be back to slurry again.
No.
what about this plus Rain-X?
Right. So waterproof is very important.
Yeah, waterproof it.
Yeah.
That might keep the CO2 from getting to it. Too,
I mean,
right?
I mean,
maybe.
there is waterproofing for. I think it's called sizing
Mhm.
for paper making process. I don't have any, but that's you can just go to Carriage House in Williamsburg to get some.
Yeah. We just found some way, to spread the resin powder into some substrate uniformly.
Yeah.
Right?
Yeah,
Yeah. You can. Yeah. Any method can work.
That's ingenious. I love that. Okay.
I love it.
Mhm.
I love it.
Mhm.
Okay.
Maybe we can put that into the bread, like some cookies. I mean, not cookie, real cookie. It's just kind of design. Yeah. Yeah.
So Tao, I had a question about the temperature. You said that if it briefly went over that temperature range, that it might be okay. I was wondering what that time period might look like, because PLA and ABS 3D printers print roughly in the neighborhood of 300 degrees Celsius to 350, depending on your print settings. And so if it was able to survive the extrusion process, that might be something that maybe not everyone would be able to do, but 3D printing a substrate that has the resin embedded might be a way to kind of mass produce this.
I'm not sure about that. We just tested our solvent using the heating oven in our lab, the oven lab in our equipment to test how long it will, be heated. So we just tested like 5 minutes or 10 minutes. We found 10 minutes would be too long. Yeah, because it damaged the material and 140 degrees. Yeah.
Would it be possible to, I don't know, like heat it up just enough and use like a vacuum former or something, like just get it softened up? I don't know.
That's what I was initially thinking when we were talking about the thermoplastic.
Yeah.
And actually, it's not a big problem for the industrial process. If you can see the pattern, you will know a lot of companies that are doing that, fabricating we call ion exchange membrane by using this process. It's not a problem for the industrial process.
Chris, I print ABS at 205. I think C.
Okay.
Which
Yeah, I know. I've only done PLA because that's what my my machine is set up for, and that's if you've got nice PLA, that's 340. If you've got like old stale garbage PLA like I have, it's like 360. But I mean, if ABS is like 200, that's that's still much closer, and like it's passing through the extruder really quickly.
Exactly.
You could test it.
Contact
I
time.
mean, but I mean that, yeah, if it can survive that amount of time. But how do you get it? How are you envisioning you get the powder into the extruder, like into the filament?
So I guess what if I were to kind of like dream this up, you would just have a separate hopper. There's a lot of like DIY 3D printing that allows you to put an additional fan by the extruder. And so you could really just have it so that it's dropping PLA from a fixed feeder onto the site where the extruder is making contact. And so you would do pass by pass. And so the downside would be it wouldn't be until the next layer of ABS is laid down that the resin would be adhered to the next surface. But you would have just kind of like an even sprinkling of the resin over the surface on the precedent step of the next layer of ABS being extruded
You could do
over.
like a dual extruder type situation where you like print a layer of plastic and then a layer of like
Right.
and then shoot out a layer. Okay.
The pie in the sky version would be the resin itself is embedded into the filament, and so whatever you print would be the ultimate sort of.
Right. You create your own.
Yeah, print a couple inch sheets.
It's like getting closer and closer to my fever dream. I'm just saying.
Yeah. Yeah.
You guys were looking at precious plastics as an inspiration, right? I mean, don't they make the machines that would let you make idealized filament?
Yeah. It's definitely interesting. If we could, that would make it much easier. Like, we would probably have to produce that filament, but if we could send that filament out to anyone with a 3D printer so they could print their own filament cartridges.
In Italy that is developed using the waste products from marble production, which is calcium carbonate essentially, and turning that into a material for 3D printing that I've tried to LinkedIn connect with a couple of times, but there's some people working on that kind of thing, so I don't know.
So efficiency aside, Tao, would it be possible for us to take something like a 20-minute epoxy, lay it over some sort of sheet, and then sprinkle the resin dust on top?
Epoxy. Oh, interesting.
Epoxy is pretty waterproof, though.
Yeah.
But since it's being dusted on top, only the portion that would be contacting the epoxy itself would be submerged under the surface, and you would have the majority of the resin surface exposed to atmosphere.
Mm-hmm.
Yeah.
I mean, this might be dumb, but I'm just thinking like double-sided tape.
Yeah. I mean, like, if you just want to flow it, like if the idea is not to have something that's embedded that you can actually get airflow diffused through, but you just want a surface. I mean,
you can calculate the loading density.
Tape.
How much? Yeah, you can calculate the loading density and then compare that with the other material. It is comparable. I think it's a nice idea.
It would have to be sufficiently supported so that as it gets wetted, right, like an exposed adhesive would wash out. But something like a resin that cures, like an epoxy.
But duct tape is not. I mean, to Kristen's point, like duct tape is made for withstanding.
Yeah.
Moisture, right?
That's specifically why I was thinking about duct tape. Yeah.
We should all pick one and run with it.
Duct tape for everything. Look.
It's on paper.
Yes.
Yeah, Tao, we need 30 kilograms of sorbent.
We need 30 kilograms of sorbent, some duct tape, some paper pulp.
Just straight up MacGyver this thing.
And some epoxy, yeah. And some old plastic bottles. Let's go.
Interesting. Do we have any questions left?
I had a question that was kind of off topic based on a conversation that Chris Neidl and I had with Serene Grama earlier this week. So I've been looking into the use of metal organic frameworks for carbon capture and or dehumidification. And so the idea is that you could take some metal organic framework, some zeolites of some type in a cartridge, and use that in a system like this to aid in the drying or dehumidification process. Have you guys investigated anything like that? Do you know anything about anyone who's using metal organic frameworks in that way?
First, I will share my idea on the dehumidifier, because we found that a very big challenge is the very high relative humidity in the atmosphere for our process. So we also did some investigation on the dehumidifier, and we found that there's one challenge is that the energy consumption to regenerate the dehumidifier, you use some material to capture to absorb the water, and then you need heat or other kind of energy to dissolve the water to regenerate material, and that energy process I calculate is very high. And so I'm still thinking about whether we really need dehumidifier, because if we use the direct air capture unit for the greenhouse, you know that the very high relative humidity generally means like cloud day or the raining day, and that also means the greenhouse need not as much CO2, not that large amount of CO2. So then maybe we can we do not also we do not very high CO2. I mean, we do not need a lot of CO2 yet under the conditions. And of course, another idea is every technology has its advantage, and it has its special application atmosphere. For the moisture swing process, maybe it can work better under some dry some dry atmosphere, right? We need to deploy the technology globally, everywhere. Yeah, so there's another kind of idea. Yeah, and then thirdly, actually, we're also developing the hydrophobic material in our lab, so that it can work better under higher relative humidity. Yeah, so that is my thinking on the dehumidifier. But yeah, currently, if we have some cheaper dehumidifier, which do not need that high grade energy to dissolve the material, that will be, I think, very helpful.
Okay.
Yeah.
Yeah, I mean, so when we were talking to him, he's, by virtue of using this sort of metal organic framework, supposedly you can use a lot less heat in order to actually do the dehumidification process. So it's actually far less costly energy-wise. We're going to get some of those numbers from him. I'm happy to share that whenever we have it.
And I, many years ago, I read a paper which they use the solvent, the CO2 solvent, to capture the CO2 and water simultaneously. And they can recycle CO2 and water, simultaneously. So I said maybe also it is an interesting thing to recycle some water, pure water, I mean, from the used mops or some kind of dehumidifier. That would be also a very interesting work. But the current mops is, I think, still very expensive.
Very expensive, yeah. I don't think anybody's producing enough of it to be meaningful yet either.
Yeah, and if you can calculate, it's for example, I think if we need a dehumidifier, if the relative humidity is over 60 degree, 60 percentage, right? Relative humidity, and then if we decrease the humidity or the relative humidity from like 70% to 40%, you can calculate the water captured from the air. It's huge, because the air velocity, the volume rate of the air is huge for the direct air capture unit. 30% of the relative humidity capture is huge for the dehumidifier. You need a lot of material, like silica gel or the mop. You need a lot of this material, and of course you need a lot of energy to regenerate the water, the solvent.
Yeah.
Yeah, because I calculated that and realized that.
Good to know. Thank you.
No.
Awesome. This is great. I mean, I don't know how to say it.
Yeah, I think there's any last questions? I don't want to keep Tao here all day, but I feel like well, I'm exhausted. But I think
Yes.
if people, some people want to keep going, but I do want to make sure that we could obviously follow up with Tao. We could get another call. We could do a follow-up email or something like that. But does anyone have any last questions they want to sort of throw out now before we wrap it up for the night?
One last question. I was wondering, Tao, if you'd observed any resin degradation over time, just from going through the cycles. Does the performance drop off?
For this material, for the ion exchange resin, it's quite stable because we said it's a cross-linked structure with the quaternary ammonium group on it. So the material is quite stable, especially in the ambient temperature. Yeah.
Will it degrade due
over
to
100 degree? Over 100 degree, it always will lose some of the properties, but in the ambient conditions, it's quite stable.
Should we be concerned about other sort of degradative forces like UV rays or anything else? Just anything that you've observed that we should try design around? One of the things that we talked about was like a clear tube, but if it's better to kind of like block light, then that's cheaper, and if it's better, that's also great.
Plastics block.
Yeah, the UV may be an issue, but actually it can be dissolved the problem can be fixed very easily. Right? It's not the PV panel is needed to receive the sunlight. Just have some cover to prevent the sun. Yeah.
I have one too. About something we talked about earlier, when prepping the sorbent to swap the chloride ion out with either a hydroxide or a carbonate, can that process be done after it's been bound with the PVC, or does it need to be this like pure pulverized? It can be done afterwards. Oh,
yes.
That makes it a lot easier. Okay.
Yeah.
Great.
And actually, I suggest that. I suggest you do the ion exchange after it is shipped.
Great.
Mm-hmm.
Seems like a nightmare to do it after you pulverize it. I was like typing the tube for hours.
Yeah.
Awesome.
Yeah, this has been amazing. Thank you so much.
Yeah.
Thank you.
It's so nice to have people who can actually ask Tao smarter questions than I can due to my tenuous grasp on chemistry, and being able to have people who have much more mastery of the subject makes all the difference in the world. So thanks Tao so much for doing this with us, and thank you everyone on the call for really taking us to this level. This is really great.
Takes a village to raise a DACC.
That's right.
Yes, it does.
Great. Awesome. Tao, thank you so much. So
thank you, Tao. Really appreciate your time. Yeah.
Thanks, Tao.
You're welcome.
Awesome.
Yeah.
Great, guys. Have a good weekend.
Thanks, everybody.
Thank you, everybody. Have a great weekend.
Yeah.
Bye.
Bye, everybody.